Hello calculus students, and welcome to the video explanation of one of the FRQs regarding Taylor series, Taylor polynomials, Maclaurin series, power series, and so forth. So let f be the function given by f of x equals 2x over 1 minus x squared. Write the first four non-zero terms and the general term of the Taylor series for f about x equals 0. So Taylor series about x equals 0, that's another way of saying a Maclaurin series. Okay. And we already know, or at least I hope you know, that a Maclaurin series for 1 over 1 minus x is simply equal to this power series. Okay. So we can, and you notice the resemblance between this series and this series here. So what we're going to do is just use this one, use this power series here to help us figure out this one. So f of x, and again, I want to emphasize we can do that because we know that a Maclaurin series in this form of this particular function is just exactly equal to a power series of x to the n. Okay? So f of x is really equal to 2x times 1 over 1 minus negative x squared. So we're going to just rewrite the f of x function to look like this Maclaurin series and then take advantage of some of the work that's already been done there. So this is really equal to the summation, this is equal to 2x times the summation n equals 0 to infinity of, but instead of using x to the n, it's going to be negative x squared to the n. And then I'm going to just continue working and simplifying this. I can bring the 2x inside because I'm just multiplying 2x by every single term. This is 2x times negative x squared to the n. And I'm going to do something that is commonly done even if it seems a little counterintuitive. I am going to pull out the negative 1 here. So this is, on a side note, negative x squared to the n is really negative 1 times positive x squared to the n, okay, which then I can separate into negative 1 to the n and x squared to the n. Okay. So I'm going to pull out the negative 1 to the n because this really tells me, makes it really crystal clear that this series is an alternating series times 2x times an x squared to the n is just x to the 2n, which is equal to the summation n equals 0 to infinity, negative 1 to the n times 2, and this is x to the 2n and x to the first, so we get x to the 2n plus 1. Now, not that any of this stuff that came before was wrong, but this answer here is probably the most convenient way because it allows me to recognize a few things. First, the series is alternating, and second, the powers of x are all going to be odd numbers. So that will help me to actually write my answer. So this is actually right here is the general term. Now I have to write the first four non-zero terms. So let's see what do I get when I plug in n equals 0, n equals 1, and n equals 2, and so on. So the first four non-zero terms. Well, if I plug in 0 into for n, that it becomes 1. This becomes 2 times x to the first. So that's just 2x. So that's simple enough. Then if I put 1 into here, I know it's going to alternate. This is going to be a negative, minus 2, that's there, and x, this is going to be x to the third. Okay? And again, this helps me to just check. Doing this extra work helps me to have this form, helps me to check that I know what I'm doing, because what should be happening is that these exponents should be all odd, because it's 2n plus 1, where n is an integer. And it alternates, so the next one is going to be 2x to the fifth, and then minus, whoops, almost wrote plus there, minus 2x to the seventh. Okay. And there we have it. That concludes part A of this question. Let's move on and let's look at part B, which says, does the series found in part A, when evaluated at x equals 1, converge to f of 1? So what we're going to do here is take 1 and substitute it in for x and see if it converges or not. Okay? So when x equals 1, we have this series, n equals 0 to infinity of negative 1 to the nth times 2, and 1 to any power. So if I put in 1 to 2n plus 1, this 2n plus 1 now is really irrelevant, because 1 to any power is just going to be 1. So I can write this out as this: n equals 0 to infinity negative 1 to the nth times 2. Okay? And now I can see that it's going to alternate. This series is just going to be alternating between positive 2, minus 2, plus 2, minus 2, and so on. So this series, we can say lots of things about this, but mainly that it alternates and does not converge. By the nth term. Divergence test. Therefore, the series does not converge to f of 1. Okay. Let's see, explained it. Okay, that's good. So now we can continue and proceed. So C, the derivative of the natural log function of 1 plus x squared is equal to this. Okay. Write the first 4 non-zero terms of the Taylor series for the natural log function. Okay, well, we're not asked to find the general term, and that saves us a little bit of work. So the problem tells us that the derivative of the natural log of 1 plus x squared is equal to 2x over 1 plus x squared. Okay? Which, using the first 4 non-zero terms, is equal to this: 2x minus 2x cubed plus 2x to the fifth minus 2x to the seventh. Therefore, if we want to find the series for the natural log function, we just take the antiderivative of both sides with respect to x. Okay. So on the left, we get that the natural log of 1 plus x squared is equal to, and the antiderivative of this term with respect to x should be rather straightforward. This is going to be x squared minus, let's see, 1/2 x to the fourth plus x to the sixth, 2 divided by 6, which is 1/3, minus x to the eighth, 2 divided by 8, which is 1/4. Now, just to be safe, we should also check that there's a constant term here, and we know that when x is equal to 0, the natural log of 1 plus x squared is equal to the natural log of 1, which is equal to 0. So if we substitute on the left side for 0, on the right side, if you put 0 in for x, you're also going to get 0. So we're going to get that c is equal to 0. So our final answer is that the first 4 terms is this. And I'm going to cross off the c here because that's really not necessary. Okay. All right, so we got through some of the more difficult stuff, and now we have one more question left that asks us to use this function that we've developed and see if we can get an estimation here. Okay, so part D says, use the series found in part C to find a rational A such that A minus the natural log of 5/4 is less than 1/100th. So this is really this is really saying like the error, okay, when estimating the natural log of 5/4 is less than 0.01. So this expression here is that I circled in red is really saying the error. Well, this is kind of tricky because we have to look at how do we represent the natural log of 5/4 using this function right here. So the natural log of 5/4 is the natural log of 1 plus 1/4. Okay? Because I want to write the natural log of 5/4 to look like this natural log as much as I can. And there's an x squared here, so I'm going to take the square root of this and then square it. So this is the natural log of 1/2 squared. Okay? So in other words, what I'm saying here is we're substituting in, and we're saying that x is equal to 1/2. Okay, so this is my way of saying that. And this is really just a note for you. I mean, I would not write something like that necessarily on the exam. So continuing down here, this is all equal to, and we have a function that we found in part C, which is 2. No, I'm sorry. It's x squared. Okay, and I'm leaving parentheses here because I'm going to fill it in with 1/2 in a minute, minus 1/2 x to the 4th plus 1/3 x to the 6th minus 1/4 x to the 8th. And we're filling this in with 1/2. Okay. And you can see here that this is an alternating series. This is 1/4. This is 1/2 to the 5th power. This is 1/3 times 1/2 to the 6th. But this is alternating. Okay. So we want the alternating error bound here to be less than 1/100th. And so if you look at these terms, well, let's see. What is this term really equal to? Well, that's 1/4 times 1/2 to the 8th, okay, which is 1/2 squared times, and 2 to the 8th is 256. So this right here is equal to 256 times 2 is 1/1024, okay, which is really small, much smaller than 1/100th. So maybe we don't need to go out that far. So maybe we can look at this. This is 1/3 times 1/2 to the 6th. Now 1/2 to the 6th is 2 times 2 times 2 times 2, 6 times, so that's 64. So this will give us 1/192, which is definitely smaller than 1/100. So what we can say then is that this term here, these two parts right here, well, let me do one more for you. Okay. So this part right here is 1/2 times 1/2 to the 4th. So that's 1 over 32. Okay. Now 1 over 32 is definitely bigger than 1 over 100, and 1 over 192 is definitely smaller than 1 over 100. So you want to take this part right here and call it A, and you want to take this right here and call it the error. And so this right here is going to be our alternating series error bound, and this is actually going to be the value of A. So we can say that A is equal to 1 over 2 squared minus 1 over 2 to the 5th. So this is equal to 1 over 4 minus 1 over 32, which comes out to 34 minus 4. No, I'm sorry, what am I doing? This is going to be 8 over 32 minus 1 over 32, so 7 over 32. Okay. So our answer here is that A is equal to 7 over 32, and by the alternating series error bound, A minus the natural log of 5/4 must be strictly less than the next term in the series, which is 1 over 192. Okay. And that sums it up. Now, we could have also used, added on, we could also use the first 3 terms here and still get the error to be less than 1 over 100, but this is one correct answer for A. So this question is kind of weird because there's more than one way to answer it, but this right here is definitely one of the ways. All right, there you have it, a very difficult and challenging question here regarding Taylor series. And if you follow through all of that and you understand it, you are in great shape. If you are struggling a little bit, as always, ask for help. Thank you for watching and have a wonderful day.